So in late 1999, NASA watched in absolute horror as their $125 million Mars Climate Orbiter just,
Uh,
well, it completely burned up in the Martian atmosphere.
Yeah, that is definitely not a good day at the office.
No, not at all. And the crazy thing here is it didn't fail because the math was fundamentally wrong or, because a thruster physically broke off.
Right, it wasn't a hardware issue.
Exactly. It failed because the engineering team at Lockheed Martin used English units of measurement for the thrust, and the team at NASA used metric.
Oh, wow, just a massive miscommunication.
Right. So the software doing the calculations was doing exactly what it was coded to do. It was flawless in that sense, but the overarching system connecting those pieces just failed completely.
I mean, a $125 million catastrophe caused by a literal failure in the software process.
Which is exactly what we're unpacking today. Welcome to the deep dive, everyone. We are looking at this huge stack of university-level notes entirely focused on software processes.
It's a fascinating topic, really.
It is. Because, as you go about your day, you're interacting with software constantly, from the alarm on your phone waking you up to the anti-lock brakes in your car. And our mission today is to figure out, how does all this invisible architecture actually get built?
Without ending up like that Mars orbiter, hopefully.
Right, exactly, without burning up in the atmosphere. So let's just jump right in.
Well, I think that Mars orbiter is actually the perfect anchor for this whole conversation. Because when you interact with software, it is so easy to just assume the hard part is typing the code.
Oh, for sure. You picture a hacker in a dark room just furiously typing green text.
Exactly. But the actual coding is, it's often the smallest part of the equation. A software process is really the structured set of activities required to develop a system.
So it's more than just the code.
Way more. It is the communication, the management, the testing, the guardrails. And while there are, dozens of different methodologies out there, the notes we are looking at today make it very clear that every single one of them rests on 4 non-negotiable activities.
Okay, let's go through those. The foundation, basically.
Right. So the first one is specification.
Which is figuring out what it should do.
Exactly. You have to define exactly what the system should do, and crucially, the constraints on its operation.
I mean, that makes total sense. You can't really build a house without knowing if the owner wants a 2-bedroom ranch or a giant Victorian mansion.
Right. You need the vision first. Then the second activity is design and implementation.
Which is the actual building part, right?
Yep. This is organizing the system's structure and actually writing that executable code. You're translating that initial specification into reality.
Okay, so we've got specification and implementation. What's the third?
Third is validation.
Like testing.
Well, yes, but specifically, it's checking that the software actually does what the customer originally asked for. Not just that it runs, but that it solves their problem.
Got it. And the final one?
Finally, evolution. Because software is never really done. It has to be modified as the customer's business needs inevitably change over time.
Okay, so those 4 activities, specification, implementation, validation, evolution, those are the ingredients.
Exactly.
But how you mix them together is where the entire tech industry splits into 2 massive, often warring camps.
Oh, yeah, it is a big divide.
You essentially have 2 main philosophies dictating how software gets made: plan-driven processes and agile processes.
Right. So in a plan-driven process, all of those activities we just talked about are mapped out in excruciating detail before anyone writes a single line of code.
Like everything is decided up front.
Everything.
Yeah.
And your progress is measured entirely against that initial roadmap.
Okay, and agile is the other side of that.
Yeah, Agile flips that completely on its head.
Yeah.
Planning is incremental, it's continuous, it is designed from the ground up to bend and flex as the customer changes their mind or the market shifts.
I always picture plan-driven development like building a physical skyscraper.
Oh, that's a good way to look at it.
Like, you absolutely need the blueprints finalized. Every single load-bearing steel beam has to be accounted for, and the foundation must be poured perfectly.
Right, you can't just wing it.
Exactly. You cannot get to the 30th floor and suddenly decide, you want a subterranean swimming pool in the lobby. The structure just won't allow it.
No, the concrete is already dry.
But Agile's more like a stand-up comedy routine.
Okay, I like this. How so?
Well, you walk out on stage with a rough outline of your jokes, but you are constantly reading the room. If a bit isn't landing, you just pivot on the fly based on the audience's reaction.
Yeah, let's take that stand-up analogy further, actually. Because the friction between those 2 approaches in the real world is immense.
I can imagine.
If you are an agile development team, You want that freedom to read the room and pivot. But if you are the corporate finance department,
Yo, they probably hate Agile.
they absolutely hate Agile. They want a skyscraper. They want to know exactly what they are getting for their $5 million budget and exactly what day it will be delivered.
Right. Agile requires a business to accept that they are funding a journey without a perfectly defined destination. That's a tough sell for a CFO.
Exactly. So in practice, most large-scale practical projects end up adopting a hybrid approach. They try to balance the predictability of a plan with the reality of a changing market.
But what if reading the room just isn't an option? What if the environment demands absolute, unforgiving predictability?
Then you need the skyscraper.
Right. And that leads us straight into the oldest and arguably the most rigid of the plan-driven models in these notes, which is the waterfall model.
Ah, yes, the waterfall model. It's the original published model of the software development process.
And it sounds incredibly strict.
It is strictly sequential. The steps flow downward, like water over a cliff, hence the name.
Yeah.
And you generally cannot start the next phase until the previous one is completely signed off.
Yeah, the notes break it down into 5 distinct phases. And honestly, the way it's described, it sounds less like software engineering and more like contract law.
It's very documentation heavy.
So it starts with requirements analysis. And you aren't just having a quick chat with the user here. You are generating a massive, detailed system specification document.
Right. And only when that massive document is approved do you move to phase 2, which is system and software design.
Allocating requirements to hardware and all that.
Exactly, establishing the architecture. And that architecture then dictates phase 3, implementation and unit testing, where you finally write the programs and test them individually.
Okay. And phase 4?
Phase 4 is integration and system testing. You combine all those individual pieces, test the whole system against that massive initial document, and deliver it.
And then phase 5 is just operation and maintenance. The system is out in the wild.
Right. But I know you have some thoughts on this.
Okay, yeah, I have to push back on the viability of this in the modern world.
Go for it.
Looking at the sheer momentum of that downward flow, if you find a major flaw during phase 4, when you are finally putting all the pieces together, you can't just fix it quickly.
No, you cannot.
You literally have to swim all the way back up the waterfall. You have to rewrite the requirements document, redesign the architecture, and then rewrite the code.
It is incredibly painful.
Testing happens so incredibly late in the process. Given how fast technology moves today, this just seems like a recipe for a bloated, outdated disaster. So my question is, why isn't waterfall completely obsolete?
It really seems like it should be, right? Especially if you spend your days working on web apps or consumer software. But waterfall survives because it is literally the only responsible way to build certain types of systems.
Wait, really? Like what?
Well, you need waterfall for embedded systems.
Okay, meaning what exactly?
So if you are writing the software that controls the fuel injection inside a car engine, you can't just push an over-the-air update easily if you get it wrong.
Oh, true. The car's already built.
Exactly. The design must be strictly defined before the hardware is manufactured.
So it's for systems where the physical hardware is locked.
Hardware locks and also safety-critical thresholds. You cannot use an agile approach for a pacemaker.
Wow. Yeah. That would be terrifying. We'll patch your heart rhythm in version 2.0.
Right. You cannot move fast and break things when writing the flight control software for a commercial airliner.
That makes a lot of sense.
For systems where human lives are on the line, you need heavy upfront documentation, strict preconditions, and verifiable post-conditions.
So there's no room for guessing.
None. It is also practically required for large multi-site government or military projects. If you have 10 different defense contractors building 10 different components of a radar system,
They need to know everything matches up.
exactly, they need complete, unchanging instructions from day one so their parts actually plug together 5 years later.
Okay, that puts it in perspective. If my life depends on the software, absolutely. Write the 500-page document and stick to the plan.
Yep.
But for the vast majority of the software you use daily, the tools we use for work, the apps on our phones, the market won't wait 5 years. And users change their minds constantly.
All the time.
So if waterfall is too rigid for the modern business environment, how do developers actually cope with that reality?
Well, they shift to incremental development.
Okay, let's unpack that.
Instead of trying to design, build, and test a massive monolith all at once, the system is basically fractured into many smaller mini-projects.
Ah, okay.
You prioritize the most critical requirements first, and those activities we talked about, specification, development, validation, they are interleaved. They happen concurrently.
So it's the difference between making your dinner guests wait 4 hours to bring out a massive banquet versus serving a multi-course meal.
I love that, yes.
With incremental development, you bring out the appetizer right away. The customer actually gets to taste it, and more importantly, they give you feedback.
That is the crucial part.
If they think the appetizer needs more salt, you can adjust the seasoning for the main course before you even start cooking it.
And the value of that early feedback, I mean, it cannot be overstated. The customer gets working software faster, the risk of total project failure drops dramatically, and it is just far more flexible.
But there has to be a catch.
There is always a catch. This approach creates its own unique friction. Specifically, something the notes refer to as maintenance debt and structural degradation.
Maintenance debt. What does that actually look like for the developers on the ground?
Well, imagine building a house by adding one room at a time whenever you feel like it, without any overarching architectural plan.
That sounds like a disaster.
It is. You add a kitchen, then a bedroom, then maybe a sunroom on the second floor. Eventually, the plumbing is a nightmare, the hallways make no sense, and the whole structure is unstable.
Because it wasn't designed as a single unit.
Exactly. In software, because you're constantly bolting on new features and changing code rapidly to meet the next increment, the system's underlying structure gets really messy.
So the code itself starts to resemble that weird house.
Yes. And unless management allocates time and money specifically to clean up and reorganize that code, a process called refactoring, adding new features, later becomes painfully slow and incredibly expensive.
The code basically becomes a Jenga tower.
A perfect description. You pull one block, and the whole thing threatens to collapse.
Wow. And the notes point out another issue with incremental development too, which is low visibility for managers.
Right, because the code is changing so fast.
Yeah, it isn't cost effective to generate a new manual or a progress report for every tiny tweak. Management just has to trust the process rather than looking at a neat checklist.
Which can make executives very nervous.
I bet. Now, a big part of dealing with this uncertainty is prototyping, right? Building a quick, rough version of a feature to see if the customer actually likes it before you commit to building the real thing.
Absolutely. Prototyping is vital for anticipating change.
But the source material is incredibly strict about one specific rule regarding prototypes, and it really threw me off.
Let me guess. The throwaway rule.
Yes. It explicitly states that a prototype must be thrown away.
Mhm.
If you build a prototype and the customer loves it and it works, why on earth would you throw away perfectly good code? It seems so wasteful.
What's fascinating here is that this is one of the most dangerous psychological traps in software engineering.
A trap? How so?
Well, to understand why you have to throw it away, you have to understand what a prototype actually is under the hood. To build something fast enough to just be a prototype, developers intentionally ignore what are called non-functional requirements.
Meaning things that don't relate to the button actually working.
Exactly. They ignore long-term security, error recovery, performance under heavy user loads, database scalability. The internal structure is literally held together with digital duct tape.
Oh, wow. So it looks good on the outside, but the inside is a mess.
Right. And the trap happens when a non-technical manager or a CEO sees the prototype. They see a button, they click it, the screen does what they want, and they say, great, it's finished, ship it to the public tomorrow.
They see the paper mache model and think it's a real building.
Yes. And if the developers are forced to use that prototype as the foundation for the final product, it is nearly impossible to go back and retroactively tune it to meet normal organizational quality or security standards.
Because the foundation is basically duct tape.
You end up with a fragile, insecure product that crashes the moment 1,000 people try to use it at once. A prototype is a learning tool to validate an idea. It is never a structural foundation.
Okay, that makes perfect sense now.
Hmm.
So building from scratch, even incrementally, takes a lot of time and carries a lot of technical risk.
It does.
What if a startup only has 3 months of runway left, or a massive corporation needs a new internal tool immediately? They can't afford to build a skyscraper, and they don't have time to cook a multi-course meal.
They have to scavenge.
Scavenge, I love that. And this introduces the third major model in the notes, reuse-oriented software engineering.
Yes, also referred to as integration and configuration. In this paradigm, the primary job of the software engineer shifts away from writing original code and entirely toward discovering and assembling existing components.
Here's where it gets really interesting. It's the ultimate IKEA hack.
Ooh, I like the sound of this.
Instead of chopping down a tree, milling the lumber, and building a desk from scratch, you just go to the store, buy pre-made metal legs, find a finished tabletop, and figure out how to screw them together.
That is exactly what it is. And the workflow reflects that shift perfectly. You start with your basic specification, but then you immediately move to software discovery and evaluation.
Looking for the table legs.
Right. You scour the market for existing components, or COS,
Yo-dep.
commercial off-the-shelf systems,
Right.
software that does roughly what you need. Then comes the critical phase, which is requirements refinement.
And this is where the friction lives, doesn't it?
Yeah.
Because if you are refining your requirements based on the software you found on the shelf, you are inherently changing what you originally wanted to build to match what is just available at the store.
That is the ultimate trade-off of the reuse-oriented model. You hit the nail on the head. The sources identify two massive compromises here.
Okay, what's the first one?
The first is requirement compromises. You might want a highly specific, totally customized sales dashboard, but building it takes a year. Buying Salesforce, however, takes a week.
So what's the compromise?
The compromise is that you don't get your custom dashboard. Instead, your company has to change its internal business processes to match how Salesforce operates.
Oh, wow. You are bending the business to fit the software rather than building software to fit the business.
Exactly. It saves time, but you lose that perfect fit.
And the second compromise the notes mention is loss of control, which sounds pretty terrifying if you are relying on these components for your core business.
It can be. You are entirely at the mercy of the component creator.
Like the company who made the table legs.
Right. If the third party who built those legs gets bought out, goes bankrupt, or just decides to completely change their API, your entire system might break overnight.
And you can't do anything about it.
You have zero control over the solution. You trade control and perfect fit for speed and a lower initial cost.
So whether a team is locking down requirements in a waterfall, sprinting through incremental development, or scavenging components for a reuse-oriented build, how do they ensure they are actually creating value?
That's the million-dollar question.
How do they avoid building the wrong thing entirely?
Well, that requires a deep dive into validation, risk management, and organizational maturity. And the crucial starting point in the notes is understanding the hard line between verification and validation.
Okay, verification versus validation, because outside of tech, we just use those words interchangeably.
We do, but in software engineering, they ask two fundamentally different questions. Verification asks, did we build the system right? Validation asks, did we build the right system?
I absolutely love this distinction. Think of it like baking.
Okay, let's hear it.
Verification is ensuring you followed the recipe perfectly. You measured the flour down to the gram, you calibrated the oven temperature, the cake rose beautifully, and it didn't burn. The system was built right.
Perfect execution.
But validation is taking that flawless cake out to the customer's table, only to realize they actually ordered a cherry pie.
And at that point, the cake is useless no matter how well engineered it is.
Exactly.
You verified the construction, but you completely failed to validate the requirement. So, to prevent the perfect cake wrong orders scenario, the industry utilizes risk-driven frameworks, like Boehm's spiral model.
Boehm's spiral model. This looks entirely different from the sequential downward flow of waterfall or the mini projects of Agile.
It really does. Imagine a spiral winding outward from a center point. Each complete 360-degree loop of the spiral represents a phase of the project.
Okay.
But the defining characteristic of Boehm's model is that it forces you to confront danger actively. Every single loop requires passing through 4 distinct sectors.
What are those sectors?
First, you set your objectives for that loop. Then, crucially, you assess and resolve risks. Then you develop and validate. Then you plan the next loop.
Wait, how does that risk assessment actually function in practice?
Well, let's say your biggest risk in loop 1 is that you don't know if your database can handle 1 million concurrent users.
That's a pretty big risk.
It is. Instead of just hoping for the best, the risk resolution phase might dictate that you pause and build a quick prototype specifically to stress test that database structure.
Ah, so you spend resources specifically to neutralize the unknown.
Exactly. Because risk analysis is baked into the DNA of the spiral, teams catch fatal flaws before they commit millions of dollars to full development.
But that level of risk management requires a highly disciplined organization. And think about the reality of the tech world, especially the startup space. Discipline is usually the last thing on the menu.
Oh, without a doubt.
The notes explore this through the concept of process improvement and the SCI capability maturity model, or CMM. It measures how mature a company's software process actually is across 5 levels.
And level 1, the initial level, is where most companies start.
And the notes say level 1 is essentially just everyone running around in chaos.
It literally is. The official definition of level 1 is that the process is uncontrolled and unpredictable. Wow. If you have ever worked at a company where every single product launch feels like a 5-alarm fire,
Oh, I've been there.
where deadlines are missed, budgets are blown, and success relies entirely on a few developers working 80-hour weeks and drinking their weight in energy drinks.
Just heroic individual effort.
Yes, you have lived in CMM level 1. It is an environment of chaotic hacking where success depends on those heroics, not a repeatable process.
So how does an organization actually escape the fire drill? I mean, you can't just mandate that everyone be more organized.
No, you can't. You escape through data. The core of process improvement is a continuous cycle. Measure, analyze, change.
So tracking things.
Exactly. To reach level 2, which is repeatable, a company has to start collecting quantitative metrics, like how many calendar days did this specific task actually take? How many critical defects were discovered in testing?
And once you track those metrics,
Once you track them, you establish basic project management procedures that allow you to at least repeat your past successes.
okay. And as you move up the ladder,
Level 3 is defined,
wow.
where those procedures become formal standards across the entire organization.
So everyone is on the same page.
Right. Level 4 is managed, where you are using advanced statistical data to tightly control the quality of the software. All the way up to level 5, optimizing, which is the holy grail.
What does optimizing look like?
The organization is using continuous feedback loops to constantly improve the process itself. It is the full evolution from unpredictable artistry and heroics into true, measurable engineering.
And that evolution really encapsulates the entire journey of these notes.
It really does.
So what does this all mean? We've explored the rigid, contract-heavy certainty of the waterfall model, which ensures the airplanes stay in the sky.
Thank goodness for that.
Right. We've seen the adaptable, rapid-fire increments of agile development, along with the very real dangers of maintenance debt and throwaway prototypes.
The duct tape architecture.
Yes. We've unpacked the Lego logic of reuse-oriented engineering and the compromises it demands, and we've seen how models like the Spiral and the CMM try to pull order out of the inherent chaos of building complex systems.
The ultimate takeaway here is that software is never just written. It is orchestrated. It is managed, rigorously validated to make sure we aren't serving cake instead of pie, and continuously evolved.
And understanding this completely changes how you view the digital world around you.
It absolutely does. The next time an app updates or a major system is delayed, you'll know exactly which process is at work or failing behind the scenes.
Like the next time a massive government tech portal crashes on launch day, or your company forces you to change how you log your hours to fit a new piece of software, you will know exactly what compromises were made.
It reveals the blueprint behind the screen.
It really does. But before we finish this deep dive, I want to leave you with one final thought to mull over.
Ooh, I like these.
If the final required activity of all software processes is evolution, meaning the system is continually patched, refactored, and changed to meet new business needs over years and years, at what point does the software stop being the system you originally built and become something entirely new?
That is a deep question.
Right. If every single line of code is eventually replaced, is it still the same app? It's the classic Ship of Theseus paradox, living right there in the palm of your hand.
A philosophical puzzle in your smartphone.
Exactly. Just something to think about the next time your phone prompts you to hit update. Thanks for joining us on this deep dive, and we'll see you next time.